Hi, this is Nasniewski. Class is Discrete Structures. We're up to section 13.2, Elementary Predicate Calculus. Let's back up. We were talking about logic. We spent a lot of time with propositional calculus. Now we're going to do predicate calculus, which is about ands and ors and stuff like that, which is about quantifiers and stuff like that. It's a short class. It's a short section, and let's do it. So, in section 13.1, we spent a lot of time writing out propositions with predicates, with quantifiers, and doing things like that. We're going to do more of that, but this time we do as we always do. We introduce quantifiers, and now we want to give you laws of when they're the same and when they're not. So that's what this is all about. So certain things are obvious, and certain things will need a little time. So basically what I'm doing now is I'm giving you rules about when different formulas with quantifiers are really the same. So, and these rules are given in the book. I do have to say, this is new things for most of you, so it's an idea to sit down and read through the book. The book is very readable. We don't do the problems that the book does, and it's worth doing. Okay? So the first thing is as follows. For all x, for all y, p of x comma y is logically equivalent, now, for all y, for all x, p of x comma y. Now, what do we mean logically equivalent? Beforehand, logically equivalent meant the same truth tables. But now with quantifiers, we're quantifying over many things. So we don't have truth tables. And the book gets a little bit formal about what it means by logically equivalent. But I just want to say it doesn't matter. Anyways, the main point here is the quantifiers commute. For all x, for all y, for all y, for all x. They're logically equivalent. Okay, let's do, we did an example. We were talking about loving. If every x loves every y, that means every y is loved by every x. It works out. Okay, next. This is logically equivalent to, and again, I'm not saying what p of xy is. I'm not saying what that is. It doesn't matter. Okay? That's the point. It works for every single p. Whatever you can say like this. Okay, so let's just see what this says. This says there is an x and there is a y such that x p of xy. Okay, well that's the same thing as saying there is a y and there is an x such that xy. Okay, the commutativity of these quantifiers. If there is such a thing and if there is such an x and there is such a y, it doesn't matter in what order you say it. Okay, but sometimes it does matter in what order you say it. Okay, and here's the one we did this in class last time. And we're gonna do it again this time when we do the problems. Okay. Main point. This goes one way. So here we have two different quantifiers, existential and universal and existential. The implication goes like this. Let's go through it. If there is an x that works for all y, okay, and we talked about this, we talked about we talked about mothers loving each child. Let's do it this way. Every person has a mother who loves them, right? So for every person, there's a mother, and the mother loves them. Okay? Now, that could be true. What this says is there's one mother who loves everybody. Well, there's one person who loves everybody. Okay? Now, that's not necessarily true. But if there was one mother who loved everyone, then this would definitely be true. Okay? If there's one person, we call them Mother Teresa. If Mother Teresa loves everybody, then everybody has one person who loves them. So this way it works. But this way it doesn't work. And we talked about it. Let's say Mother Teresa doesn't exist anymore. Still, this could be true and this could be false. Everybody has a mother who loves them doesn't mean that there's one person who does it. So here's one person who satisfies this formula. If there's one thing that satisfies this formula, it doesn't. It means that it satisfies for everybody. But it could be everybody has a different one, and it doesn't necessarily mean that there's one person to satisfy it. We did examples of this last time. We're going to do more examples in both in this section and in the next. Okay, great. And in the homeworks. Okay, next. Okay, the main, okay, so let's erase this because this is very nice, but we need more room. Okay, the next thing is as follows. Let's say we're talking about the students in this class, and I want to say there is a student in this class that's happy. Okay, we're going to go with an easy example. There is a student in this class that's happy. So another way of saying that is Jack is happy, or Jill, happy Jill, or happy Bob, or happy, or happy John. Okay, so saying there is somebody that is happy is the same thing as saying this person's happy, or this person's happy, or this person's happy, or this person's happy. It could be a few people that are happy, that's fine, but one or the other is happy. Okay, so that's kind of the same thing. Now, this is for a domain of discourse which has a finite number of elements. So I can list off the finite number of elements. However, if we're talking about the real numbers or something like that, or the natural numbers, then I can't really do this because there'd be too many. You can't do it for all possible numbers. Okay, so that's fine. I want you to just keep in mind that existential quantifier is like a lot of ors. Okay, there are like a lot of ors. Great. Let's now get the other intuition. If I say for all x, h of x, what does that mean? Everybody in the class is happy. Well, that really means h of that Jill is happy, and h of Jack is happy, and h of Bill is happy, and and h of Joanne is happy. So what does it mean for all x, h of x, everybody's happy? That means this person's happy, and this person's happy, and this person's happy, and this person's happy, and this person's happy. Okay? Everybody's happy. That means and, lots of ands. So what I want you to get out of this, the intuition, is that universal quantifier is just like a big generalization. It's like a super operation of a lot of ands. Keep that in mind. Okay. Okay. Now, with these two intuitions, you can understand why this was true. For all x, p for all y, okay, p of x comma y is the same thing as for all y, for all x, p of x comma y. Okay, you can see why it's the same thing, because basically this is a lot of ands, and 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 you saw p and q is logically equivalent to q and p. So it doesn't matter what order you write all your ands. That's the main point. That explains that. Okay? Similarly, you could swap the order, the order of this, and it doesn't really make a difference because this just is a bunch of ors and this is a bunch of ors, and it doesn't matter what order your ors are. That's because of this rule, and so it doesn't really matter. Great. Now the other thing, the intuition with the third rule we wrote, that's a little bit harder to understand, and I'm going to skip it. I'm not going to skip it, we're just not going to talk about it. But now I want to talk about another intuition of another rule that you've already seen, but you've never seen it in this form. And it goes as follows. It's false that for all x, p of x is logically equivalent to there exists an x such that not p of x. Okay, so before we do the intuition, before we give a name, let's just do an example of this. Okay, so you might want to put this like this. Okay, let's do an example of this. And the example is, let's say, it's false that everybody in the class is a Democrat. Okay, it's false that everybody in the class is a Democrat. What does that mean? That means there is somebody in the class who's not a Democrat. Okay? If it's not true that everybody's a Democrat, then there must be a Republican, right? No independents. Okay? If it's false that everybody in the class is a Democrat, that's the same thing as there's somebody in the room who is not a Democrat. He's a Republican. Okay? Goes the other way too. If there's somebody in the class who's a Republican, that means it's false that everybody in the class is a Democrat. Okay, great. Okay, but I want you to think of this now in terms of the ors and the ands. Let's see what this says. This says, let's imagine there are 3 people in the class. Okay, so let's say it's false that p of, let's say the first person in the class is A, okay, and universal quantifier. The second person in the class is B, and universal quantifier. The third person in the class is C. Okay, so it's false that A is a Democrat, and B is a Democrat, and C is a Democrat. Okay, but we know how to do this with something we learned before. This is the same thing, logically equivalent to what? It's false that A, or it's false that B, or it's false that C. Okay. Let's say it like this. If it's false that A is a Democrat and B is a Democrat and C is a Democrat, that means A is not a Democrat, or B is not a Democrat, or C is not a Democrat. What rule should we call this? And we know what we call it. We call it De Morgan's law. Okay, great. This is if there are 3 people. Okay, if there are 3 people. But obviously, we can do it for any domain of discourse, any universe of discourse, as big as you want. So let's see what this says. This says if it's false that everybody's something, then there is something that's not it. Okay? And we call this De Morgan's law. Okay? We had De Morgan's law by set theory when we were talking about union and intersection. We had it by propositional logic when we talked about and or. And now we have it with predicate calculus when we talk about these. Let me give you some other forms of De Morgan's law. De Morgan's law comes in different forms. So here's another one. it's false that for all, sorry, we did that already. I'm getting frustrated with the okay. This is logically equivalent to for all x not p of x. Okay, let's do this with Republicans and Democrats. If it's false that there is someone in the class who's a Democrat, that means, let's say it again. If it's false that there is someone in the class who's a Democrat, that means everybody in this class is not a Democrat. Okay, let's do that again. If it's false that everybody in the class, if it's false that there's someone in the class who's a Democrat, okay, if it's false that someone in the class is a Democrat, that means everybody in the class is a Republican. Okay, let's do it another way. If everybody in the class is a Republican, and that means it's false that there exists a Democrat. And you can do the exact same thing. Sit down and do it for 3 people. Assume there are 3 people. P of A, P of B, P of C. Here inside you're going to have ORs. Okay, and you're going to negate the ORs. Negating the ORs is the same as having lots of ands of these. Okay, so that's a second version of De Morgan's law. Let me redo this. Okay? Okay. Let's do this first. Okay? Let's take this and negate this. If you're going to negate this, this is logically equivalent to this, so we're going to negate this. So we could do this again, another way. So if I say for all x, p of x, another way of saying for all x, p of x is it's false. I'm just negating this. Not is the same thing as leaving it alone. Okay, and I'm putting the not over here. It's false that for e of x, not p of x. Okay, let's see what this says. If everybody in the class is a Democrat, that means it's false that there exists a non-Democrat. Say the exact same thing. If everybody in the class is a Democrat, that means it's the same thing as it's false that there exists a non-Democrat. It's false that there exists a Republican. Okay? Great. Let's go this way. If it's false that there exists a non-Democrat, that means everybody in the class is a Republican, is a Democrat. Okay? Let's do this. Now I'm going to take this line and I'm going to double negate. I'm going to put a not on here and a not on here. And so we get it like this. Okay, let's do this. You ready? If there exists somebody in the class that it's a Democrat, that means it's false that everybody is a Republican. Let's do that again. If we say there exists someone in the class who is a Democrat, that means it's false. It's false that everybody is a non-Democrat. Okay. Main point is you can write these quantifiers in terms of the other quantifiers. All 4 of these are just coming from the same idea of De Morgan's law. They're all the same idea as De Morgan's law. Okay, great. Okay, now I do some problems. Some of them overlap with the homework problems. Okay, that's it. That's the end of teaching of this section. That's the only thing we did in terms of teaching. But I want to go through some of these problems. Okay, so let's do 4a. Okay, and then we're going to, for homework, we're going to do all of 4, but here we're going to do 4a. So P of m comma n means m is not equal to n. Okay. The domain of discourse is the natural numbers. We're talking about the natural numbers. Okay, give the truth of each of the following. Okay. For all n, there exists an m such that I'm not going to write this. I'm going to write this so that we don't have to do this. Okay, there exists an m such that for all n, m is not equal to n. Okay, now we want to analyze this. We want to know, is this true or is this false for the natural numbers? Okay, great. In order to analyze an arrow, we have to see what this is, if this is true, and then we see if this is true, and then we see, okay, how the arrow works. Question, is this true? For every n, for every number in the natural number, is there another number, is there a number m, such that m is not equal to n? Okay, and the answer is yes, this is true. This is damn true. Okay, give me a number. 55, well, 59. Give me a number. 128, well, 42 is not equal. So there's always another number that's not equal to. How about this? Is there a number m such that for all n, m is not equal to n? Is there some number that no other number is equal, or not, I should have said no other number? Is there some number that nothing is equal to it? Okay, and the answer is this is false. Okay, why is it false? Okay, because pick any number, 53. Well, I can't say that every number is not equal to 53. So this is false. Now, true arrow false is, let's do it this way, 1 arrow 0 is 0. So this is a false statement. Okay? We're going to do the rest of 4 when we do the homework, but this is a nice problem. I think the odd numbers are done in the back of the book. That's why I'm sticking to mostly the evens. So you can do the odds on your own. Okay, great. Number 6. So now we're doing 6. Let's read 6. 6. Show that the logical implication okay. Again, I'm confused with why I did this here and not do it in the thing. Okay, let's do it like this. Okay. Before we do 6, let's do another problem. I mean, it's related to it. Sorry. Sorry, that's an X. Okay, great. There exists an x, p of x, or there exists an x, q of x. How does that relate with there exists an x, p of x, or q of x? Okay. Okay, so here we're talking about the relationship between exist and or. Exist and or. Okay. Okay, let me just give you an example. Let's say there is somebody in the class who's rich, and there's somebody in the class who's handsome. Okay? We're talking about boys handsome, not girls. Girls are pretty, boys are handsome. There's somebody in the class that's rich, or there's somebody in the class that's handsome. Does that mean that there's somebody in the class that's rich or handsome? Well, if there's somebody in the class who's rich, then this would be true, and that same person would make this true, and so this would be true. So, well, you just need one person that's rich, and this is true, and therefore the OR is true. So, and that thing implies this. If there's one person in the class that's, let's say, handsome, okay, then this is true, and therefore this is also true, and that implies this is true, okay? But it goes the other way around. If there's one person in the class who's rich or handsome, that means that whatever he is going to satisfy this. So this is satisfied. Okay. Another way to see this is a bunch of OR statements. This is a bunch of OR statements. This is a bunch of OR statements with an OR in between it. This is a bunch of OR statements. So they're all mixed up OR statements. There are a lot of OR statements that you can rearrange to get from one to the other because it doesn't matter how you do the OR statements. Great. Now let's get back to problem number 6. How about this? There exists an x, p of x, okay, and there exists an x, q of x, okay, and there exists an x, p of x, and q of x. Okay. Question. What implies what? Let's do this. Let's say there's somebody in the class that's rich, okay? And there's somebody in the class that's handsome. There's one guy that's rich and there's one guy that's handsome. Does that imply that there exists one person who's rich? Does that imply that there exists somebody who is rich and handsome? Okay? God doesn't give out his gifts evenly. Okay? So it could be that there could be one person who's rich and one person who's handsome, but that doesn't mean that there's one person who's rich and handsome. That's not true. Okay? So this way is false, but this way is true. Okay? If there's one person in the class who's rich and handsome, okay? If there's one person in the class who's rich and handsome, that means there's somebody in the class that's rich and there's somebody in the class that's handsome. Happens to be the same person, but it doesn't matter. This will be true and this will be true. So in this case, one of them is true. The point is that the ands and the ors don't mix as well as the ors and the ors. Okay, great. You know what? Let's do, so let me read the problem first. Show that the logical formula, this implies this, that's what, show that this way is false. You do this by defining predicates P and Q where the implication fails. Do the same for the logical implication that. Compare this, okay. Okay. We're going to do this in a second. Okay, I just want to do the same thing for the ands also. The universal quantifiers and the ands. Okay, it's not part of the homework, but I want to do the same thing and get used to it. For all x, p of x, and for all x, q of x. Okay, question, what's the relationship between that and for all x, p of x, and q of x? Okay. Now notice, universal quantifiers is a bunch of ands. Here's an and, here's a bunch of ands, here's a bunch of ands. Everything here is ands. Okay, conjunction. Okay, let's say this. Everybody is a Democrat and handsome. Does that mean that everybody is both a Democrat and handsome? And the answer is yes. If everybody is this and everybody is that, then everybody is this and that. Okay? But it goes the other way too. Okay? If everything in the universe of discourse satisfies both of them, then everything in the universe of discourse satisfies one of them, and everything in the universe of discourse satisfies the other one. Great. So what this says is that universal quantifiers and conjunctions and get along very well. Okay, let's do the other one. For all x, p of x, or for all x, q of x, for all x, p of x, or q of x. Okay, let's go through this. Okay, let's do handsome and handsome and what did I say? Smart and rich and handsome. Okay, if everybody is either handsome or rich. I'm sorry, I said rich or handsome. If everybody is rich or handsome, okay? Some people are rich, some people are handsome, some people are both, some people are one. Okay? Everybody is rich or handsome. Does that mean that everybody's rich or that everybody's handsome? And the answer is no, it doesn't mean this. This is false. Okay? Because it could be that some people are only rich, and it could be, and some people are only handsome. Let's say God gives out his gifts evenly, okay? In that case, some people are rich, and those who are not rich are handsome. Okay. Now, that doesn't mean that everybody's rich, and it doesn't mean that everyone's handsome. So, this is false, okay? But this is true. Let's do this. If everybody's rich or everybody's handsome. Now, if both of them are true, then this is definitely true. But even if let's just say that it's a rich class and everybody's rich. Some people are handsome, some people are not. We don't care. But the main point is, if everybody's rich, then everybody is rich or handsome. Yeah, because they're all rich, so it's going to satisfy this. So this goes this way. Okay. Okay, let's do number 8. I'm going to do 8a. I'm sorry, just 8. Okay, this is just 1 8. Okay, and oh, and we do 7 in the homework. Okay, so it says write the negation of this formula without using the connective and not. I'll explain to you in a second. First, let me copy it. So they give you a formula. There exists an x such that for all y there exists a z such that z is greater than y, arrow, oops, z is less than x squared. Z is less than x squared. Okay. Now, listen to what they want. Listen to what they want. Write the negation of this without using the connective and not. Okay, so they want you to take this and they want you to do the negation of that. Okay, now write this, but don't have that symbol. Okay, so now what we're going to do is a lot of examples of De Morgan's law. Because what does De Morgan's law do? It brings the negation in. So let's bring the negation in. So this becomes like this. This is going to go here. This is going to become for all of x, and then there's going to be a not over here. But one second, we can bring that over here. We're going to bring that not over here. So this becomes for all x, and what is, again, what is De Morgan's law do? When it crosses in, it changes from an existential quantifier to a universal quantifier. When this dot crosses this for all y, it's going to become an existential y. Okay? And then we're going to do it again, and it's going to become a for all z. Okay, so we're going to have for all z, and then we're going to have this not statement, and it's going to be z, z greater than y, arrow, okay, z less than x squared. Okay, great. So we have no negation here. We have one here. Okay, great. What does it mean that this should be false? What does it mean that the arrow should be false? Well, it means that this is true and this is false. So I'm going to write it like that. Again, what does it mean? We want this statement. We're saying it's not true. The arrow is not true, which means, so what does it mean it's not true? It means this is true and this is false. Okay, that's the only way you're going to do it. So we're going to write this as follows. For all x, there exists a y such that for all z, okay, and now we're going to do it as follows. Z greater than y is true, but z, sorry, stop. This is true, and it's not true that z is less than x squared. Okay. Now, there is no knots over here. There's only one knot over here. Okay, great. Hold on. Great. Now, this is perfectly fine, but they don't want the negation symbol. So how can I write this without a negation symbol? And the answer is very simple. This is the final answer. For all x, there exists a y such that for all z, box, z is greater than y, and instead of writing z, it's false that z is less than x squared, we could write z is more than or equal to x squared. Okay, so everything's done. Now there's no negations. There's no not sign. Okay. Okay. So that takes care of that. Very nice. Lots of problems. The book is into this for some odd reason. How do you write something without negation signs? But anyways, that's a nice problem. Okay, next we do the homeworks. Again, try to do the homeworks by yourself before you look up the answers. Take care.